Hello, chemistry. Real quick, I think I'd like to show you a little bit about Dalton's law of partial pressures. Now, when we say partial pressures, that's because the total pressure of the gas in a system, we'll call that P total, is really composed of the pressure that is being put on by each of the individual gases. Okay, so as an example, the P total for our atmosphere at at sea level and 0 degrees Celsius is going to be, let's say, 1 atmosphere. Let's do it in atmospheres. Okay, now we know that our 1 atmosphere is made of 78% nitrogen, 21% oxygen, and 1% other. So that could be, of course, just about anything. It's partly helium, it's partly ozone, it's partly sulfur dioxide, whatever stuff's floating around. So, but that tells us, what Dalton's law tells us is that P total equals the pressure of the nitrogen plus the pressure of the oxygen plus the pressure of everything else. And together, they're going to create that 1 atmosphere. So if I know that I have 1 atmosphere of pressure, that's regular, just air. Okay, so here's our number unit substance. I know that I've got 0.78 atmospheres of nitrogen. I've got 0.21 atmospheres of oxygen, and I've also got 1% or 0.1 atmosphere or 0.1 atmosphere, 0.01, excuse me, of other. Okay, so correlations I'd like you to make here is if P total was the 1 atmosphere and this is 78%, then that is where we got the 0.78 atmosphere, because 78% of 1 atmosphere is going to be 0.78 atmospheres, and that should make some sense to you. Now what we can do with this is we can take this 0.78 atmospheres N2 and let's figure out how many moles that is. So 0.78 atmospheres of N2 let's see, that's the P1, or that's P. The V, let's keep it at STP, and let's go 22.4 liters. So we're going to deal with the kind of our STP per vnert 1 mole thing. Okay, we don't know the number of moles. We've got we're using atmospheres over here. So for our R value, we're going to need to use 0.0821 liter atmospheres per mole Kelvin. And the temperature we're going to say is at 273 Kelvin. Just to keep everything kind of in an STP. Alright, so divide both sides by 0.0821 times 273. And here is the liter atmospheres, which I haven't done this for you yet. Liter atmospheres per mole Kelvin. And this is kelvins. You can see that kelvins cancels kelvins, atmospheres cancels atmospheres, liters cancels liters, moles is the only unit that didn't cancel, and therefore that is what we are going to be solving for right here. So divide both sides by the same, and then all of a sudden N equals, I don't know, whatever that math is. Find out how many moles of nitrogen are actually there. So it'd be moles N2. Now, if I wanted to figure out how many moles of each thing there, or each substance there is in this particular gas sample, I would go through the same process for oxygen, and then one for, say, carbon dioxide or something that was making up that 1% other. And then I would be able to add all of these moles together, the moles of N2, the moles of O2, the moles of CO2, and there I'd be able to get the total number of moles. So, in a nutshell, that's Graham's law, or excuse me, not Graham's law, that's Dalton's law of partial pressures. Okay, now the next one is Graham's law. Okay, and Graham's law is all about rates of effusion. Okay, so for something to effuse, you need to have a small opening for the stuff to leak out of, essentially. So if I have a whole bunch of molecules over here, and you can see that some are bigger than others, these small little dots are going to have a much easier time leaking through this passageway right here and weaseling their way over into the other side. And the bigger ones are going to have a harder time. They're going to have a harder time fitting. They're going to have a harder time moving, because if we have, let's say, 273 Kelvin temperature here, that is a set amount of energy that these all have. If I put 1 Newton of force on this little guy and 1 Newton of force on this bigger guy, this little guy is going to move a lot faster than the other one. It's going to bang around more often, it's going to hit the sides, and it's going to accidentally find its way through that little tiny hole at a greater rate. The bigger one is going to be lumbering, and it's going to bounce and bounce and bounce and bounce and bounce and bounce and bounce, 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 bounce. But the little guy is going to bing, 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 bing. Way easier to move around, okay, with a certain amount of energy. And that's basically what Graham's law gives us. So as you can hear, I'm grabbing my Chem Bible out of the desk drawer so I can write down Graham's law. On here you should be able to find it. It's the one that says rate A over rate of B equals the square root of the, let's see, what is that? Molar mass of B. So on your Chem Bible it has M times W. Okay, it's the molar weight, I think is what they're trying to say there. But it is the molar mass of B over the square root of the molar mass of A. Alright, so if you're trying to find out how fast one goes, you basically take the mass of one over the mass of the other. So the rate will be, let's say that this is a particle B right here, and this is a particle A right here. We'll say the mass of A is really tiny. Let's put a 0.04. Let's go 1.04, just for the sake of doing it. Okay, and the mass of B, let's say, is, let's call that 5. Okay, and that's grams per mole, of course. It'd be the same on the bottom, but I'm running out of space to write it. So what I'll do is I'll take the square root of 5 divided by the square root of 1, which I'm doing right now, and that gives me a 2.23. You know, what is that 2.23? Well, it's 2.23 over 1. So this is B, and this is A. And so what you're getting here is a ratio of effusion, a ratio of the amount of or how fast the small particles are going to leak out of that hole compared to the big particles. So it is the rate of B to A. So it's a 2.23 to 1 ratio. And that is essentially Graham's law in a nutshell. If you have any other questions, please feel free to post them on this, especially, so everybody can read them. And we will have some opportunities to practice this also, both of these things. All right, thank you.